Hi, my name is Ngo Chun Tong. Now I'm giving a presentation of second derivative test. Okay. In this presentation, I will introduce the theorem. Also, I will also give a proof for this theorem. After that, we'll see an example and application. This application is I will find two research papers that using second derivative test. The second derivative test. Let O be an open subset of Rn that contains the point x, and suppose that the function f has continuous second order partial derivative. Assume that this gradient vector is equal to 0 vector. If the Hessian matrix is positive definite, then X is a local minimizer of F. If Hessian matrix is negative definite, then X is a local maximizer of F. This Hessian matrix that I will state it later. If the matrix is indefinite, then this X is a saddle point of this function. Saddle point, this means that this F is not positive and also not negative as like this. Okay, now we see this graph. We can see that this point is a local minimizer. For this is a local maximizer. But for this, if we see this with this direction, you see this curve, then and here is a local maximizer. But if you see this graph with this direction, we can see this curve here, and this point here is a local minimizer. So this point is as a local maximizer and local minimizer is, and also the point is cannot be local maximizer and local minimizer at the same time. So in this case, we will call this saddle point for this. Okay, before we prove a theorem, we need some lemma. Okay. Let O be an open subset or subset of Rn that containing the point x, and suppose that f has continuous second order partial derivative. Then we have this limit. Here is the second Hessian matrix. You can see that this Hessian matrix is a matrix with second order partial derivative. Now for the definiteness, let A be an n by n matrix. It is said to be indefinite provided that the inner product of AU and U is larger than 0 for some U, and inner product of AV and V is less than 0 for some V. Theorem show is let A be a n by n positive definite matrix, then there is a positive number C such that this inner product is larger or equal to C times the square of norm U. We need to be careful here is the U is for all U in Rn. Okay, now we start the proof. Let X in this in O and axis are larger than 0 such that this ball is inside this O. Okay, from the lemma above, we know that we have this. First, we have to state it. I forget to state it. F has continuous second order partial derivative. Okay, then we have this limit. Okay. We also need f x is 0. So we can see that this part here is 0 with inner product with a vector. Obviously this is 0, so we can ignore this term in the later part. Okay. Now we consider few cases. For the case 1 is the Hessian matrix is positive definite. Just now I already mentioned that this is positive definite, then x is C larger than 0 such that this inner product is larger equal to C times the norm H squared. But just now it's U. Now I use H. Since we have this limit, so we can use the epsilon delta definition of this limit. Here we choose the epsilon for CO2, which is positive. Then we have this absolute value. The 0 is come from here. Is less than epsilon is equal to CO2. Okay, we expand out this absolute value, then we get this. Now we consider on this part. Okay, we move everything to system to this side, then we have fx plus h larger than this blah blah blah. Okay, here we have this term. Okay, just now we said that epsilon is equal to c over 2 here, and also this inner product thing is larger or equal to c times the norm h squared. Now we have this fx minus this plus this. This is equal to 0. So we have fx plus h is larger to fx. So we can see from here, we can see that x is the local minimizer inside the ball. Okay. Now for the case 2, is the Hessian matrix is negative definite. Here we define a new function gx is the negative fx. So we have the Hessian matrix of gx is negative Hessian matrix of fx. So now we can see that this Hessian matrix of gx is positive definite. From we do the same step from the case 1, we get that gx plus h is larger than gx. So we can see that x is a local minimizer of g, and since we have g is negative f, x is also a local minimizer of f. Okay, now for the case 3, is the Hessian matrix is indefinite. Since the Hessian matrix is indefinite, at least u1 and u2 is non-zero, such that this c1 is equal to this inner product larger than 0, and c2 is the less than 0 thing. Here we assume that u1 and u2 be the as norm 1. If the norm is not 1, then we divide by its norm, then we can get 1. Okay. Here we also use the limit from just now, and also we just ignore this term. Okay, for all epsilon, here in this line we just apply the epsilon delta definition for this limit. Okay, here we just epsilon. Now we just epsilon to be negative c2 over 2. From here we can see that c2 is less than 0, so negative c2 over 2 is positive. Then we write everything from this. Then we have fx plus h minus fx less than negative c2 over 2 this plus this thing. Now we define h1 to be k1 times u2. Here we can see that the norm of h is less than delta prime here, and also this is less than delta 1 prime. Here is no have prime here. Yes. So after we cut half of it, then we choose the minimum of them, and then we have this h1 is less than delta, and also h1 is less than delta 1 prime. So we have this is less than minus c2 over h1 square plus c2 over 2 h1 norm square, and this is equal to 0. So we get this. So we can see that in this fx is a local minimizer. But now we consider another thing is the epsilon is equal to c1 over 2. So the step is almost same with this one. Then we get the fx plus h2 larger than fx. Here the h1 and h2 is the vector, not h1 h2, is x plus h1 and x plus h2 is inside the ball. So maybe like x here, x plus h1 here, and x plus h2 here is inside this ball. And we can see that fx is not a local maximizer, no, local maximal and local minimal. So this is saddle point. So now we have already end the proof. Now we see some example. Consider this function fx equal this thing. Now we want to show that this 0, 0, 0 is a local minimizer of f. So as a condition, we need to check the condition. F has continuous second order partial derivative. This is obviously because f is a polynomial function. Okay, we also need that the gradient vector is 0. Now we find the gradient vector and we sub the x here inside, then we get this 0. Again, how here is the Hessian matrix, and we sub the point inside, then we get the 3 by 3 matrix. Now we want to determine this matrix is positive definite or negative definite. Here we use the method is we find the eigenvalue. Okay, to find the eigenvalue, we can solve the characteristic polynomial. The polynomial is here, and the graph is like this. This is a cubic function, so we can see that the graph is like this. So this graph is very big, very large. So I will capture part of it. You can see that this 3 point is at the right side of this y-axis. So these 3 are positive. So we can say that the roots of px are positive. So the Hessian matrix here is positive definite. So 0, 0 is a local minimizer of f. To find the minimum value, we just sub the 0, 0, 0 inside the function. So we get 0 here. It's a local minimum. Okay, for the application, I found that this has 2 research papers that using this theorem. First is a strong second derivative test. Here is the paper, and here we use this. I need to introduce a definition here is for dense 0 of a function g. This is a point such that any interval containing x0 contains a 0 of gx other than x0. That is, x0 is a limit point of the 0 of gx. But here is the second derivative test. Use it. Okay, if f prime, actually we can see that this is the gradient function 0, and here's the another condition. Then we have see that x0 is a strict relatively minimum if and only if the second derivative is larger or equal to 0 inside the neighborhood of x0. So x0 is strictly relative maximum and only if second derivative is less or equal to 0 in this neighborhood. Okay, x is an inflection point if and only if the second derivative change sign at x0. Okay, this is for the first paper. Okay, now for the second paper is on the second derivative test for constraint local extrema. Is this. Okay, this we need to find the local extrema with some constraint. Here the constraint is let that FGA will map the U to R be differentiable function for alpha in 1 to n. Okay, the constraint here defined to be the equation that G alpha is 0 for alpha between 1 to n. Okay, in this paper we will determine the local extrema for the function f a to r, where f this is the restriction of the function to a solution set A. Now I will go to the part of use this theorem on here. Second derivative test. Okay, suppose that V is inside this set is a critical point of the Lagrangian function. Here is another condition, an assumption, and here is similar to the gradient function equal to 0. Okay, now we see the statement. If the sequence this thing is positive definite, then subject to the constraint f is local minimum this u. For the next one is the sequence is negative. If the sequence is negative definite, then subject to the constraint f has a strict local maximum. Okay, and another is the sequence is non-trivial. Actually, we can see that this non-trivial, we can think it as indefinite. So this is the saddle type. We also can say that saddle point in our proof. Okay, after that we can see that the order gives some example here. Okay, now I come back here. Okay, the conclusion is this second derivative test is a very powerful test that you can use to find a local maximum, minimum, or saddle point for a function. It's also used by mathematicians in doing research. Okay, thank you.